Hi friends, welcome to GMK tutorials. In this video, we are going to see about the leakage power minimization. It is one of the most important concepts in the low power VLSI circuits and concept point of view. Okay, let us move on to the why leakage power is very important, why we are reducing the leakage power. Okay, suppose if you are taking a So let us consider this is a size of this chip. Size of the chip in the previous stage. But as the technology goes on increasing, the size of the chip is reduces to very small size. That means if you are reducing the size of the chip, obviously the supply voltage to this one is VDD. Let us consider in this case, this voltage may be scale down to maybe VDD by 4 or VDD by 2. So depending upon the requirements of the corresponding chip. So what happens is that if you are reducing the supply voltage, obviously let us consider in this situation the threshold voltage VT is the threshold voltage. As if you are reducing the supply voltage by 4, obviously the threshold voltage is also decreases. So the problem is arises here only. What does that problem mean, sir? If you are reducing if VT threshold voltage is reduces means that obviously leakage current is increases. That is the basic problem. So what happens if the leakage current is increases? Generally you know that power is P is equal to generally I square into R, right? That means I is nothing but current, right? If the leakage current is increases means that obviously total power dissipation is also increases. Moreover, as per the statistics, this leakage power is in case of the 90 nanometers technology, this leakage power is around 42%. But if you go for the 60 nanometers range, this is increases to 50% of the total power. Okay, that's why it is very important. You have to consider this one is very important. So let us move on to the first one. Due to the aggressive scaling of the low power VLSI domain, the designing of the chips from millimeters range to nanometers era. So that is the first point. As well as the performance improvement is continuously achieved by using the corresponding different techniques in the low power VLSI concept by reducing the gate capacitance. If you are reducing the gate capacitance, obviously the performance is also increases. Moreover, this gate capacitance is also related to the threshold voltage. That is the one more problem actually. So moreover, if the supply voltage must continue to scale the device scaling to maintain a constant scaling, the threshold voltage of the metal oxide should also scale at the same rate. That means we are familiar with why we are reducing the device future size. If you are reducing the device future size in case of the supply voltage scaling, that is nothing but unit number 3, we have to maintain a constant field in the corresponding circuit. That is also one of the most important aspect if you go for the low power VLSI concept. So for that purpose, if you want to maintain minimum field, constant field, you have to maintain the corresponding ratio of VCC by VT is also some very appropriate manner only. As well as what happens is nothing but if you are reducing the threshold voltage VT value, it exponentially increases the leakage current. That is also one more problem. As well as if you go for the 90 nanometers technology, this leakage power is 42% of the total power. But if you go for 65, this is around 52% of the total power. That is also one more drawback. So that's why we have to minimize this leakage power to as far as possible. Otherwise, this leakage power is also one of the major power dissipation in case of the total power conservation point of view. So let's move on to the next one. So this graph shows that how these subthreshold leakage current and delay are very related. So as the supply voltage is scaled down, delay of the circuit is increases. Why delay of the circuit is increases? Generally Generally, you know guys, delay is directly proportional to VDD by VDD minus VT whole square. This is a formula for delay. So that means if you are decreasing the delay value, supply voltage, obviously delay is also decreases. Suppose if you are let's see here, the situation is like this. So this is a very consideration. So as the supply voltage is scaled down, the delay of the circuit is also increases. So let us see why. Delay means that delay is directly proportional to VDD into by VDD minus VT whole square. So this is a formula. That means if you are reducing the supply voltage, obviously this factor is also very small. So that's why this component is increases, therefore delay value is increases. So that is a basic reason. So that means if you are reducing the supply voltage, obviously the delay is also increases. As the delay increases, what happens is that the speed of the system is less. Speed of the system is less. That is one more problem actually. Suppose if you want to maintain the speed of the system, what is another parameter? So if you want to increase the speed of the system more, threshold voltage must be decreases. If you are decreasing the threshold voltage, there is a possibility for reducing the supply voltage. There is a possibility of if you are reducing the threshold voltage, how can you achieving this one? By reducing the supply voltage. If you are still reducing the supply voltage, some more consequences we are facing in case of third unit, right? Like if you go for the MVS concept as well as DVS concept. Now we are just focusing on why we are reducing the sub-threshold leakage current is very important, right? Let's move on to the next one. So this graph shows that threshold voltage versus sub-threshold leakage current. So this is nothing but threshold voltage, this is nothing but sub-threshold leakage current. So this is nothing but if the threshold voltages are increases, obviously leakage current is decreases. That means this is the current direction. So the current value is decreases as the threshold voltage is increases. That means from this conclusion, this graph shows that if you want to reduce the threshold voltage, you have to increase the threshold voltage. That is the one point. So this limits to advantage range of supply. So the delay can be kept constant if the threshold voltage is scaled to same ratio. Unfortunately, the threshold voltage is scaled down, supply is increases in the figure. So that is nothing but very important from this one. As well as this graph is also shows that threshold voltage versus delay of the corresponding current system. Suppose if the threshold voltage is from 0.8 to 0.2, obviously the delay is also decreases. So that is also very important. If the delay is decreases, what happens? The speed of the system is increases. That is one of the advantage point from the threshold voltage. So from the threshold voltage, we have two benefits is there. One is nothing but if you are reducing the threshold voltage, so from these 2 points, threshold voltage is decreases, delay decreases. As the delay decreases means that performance increases. As well as if you are increasing the threshold voltage, the leakage current is decreases. These are the two important points from this two slides, right? So you have to keep these points very important for next analysis also. You have to remember always these two important points. What happens if the threshold voltage is increases and what happens if the threshold voltage is decreases, right? Let's move on to the next one. So that means if you want to generally previously just to have to maintain only one threshold voltage in the one circuit. So you need multiple voltages, multiple threshold voltages are required because of we needed two threshold voltages are very mandatory to maintain a performance point of view as well as power reduction point of view. So that's why before going to the how we are approaching the leakage power reduction, instead of that one, how to design the multiple threshold voltages and what are the techniques are available for the multiple threshold voltages point of view. Let's move on to the that one, then we will go to the how we are going to minimize the leakage power reduction concepts. Okay, so let's before this is nothing but just a very brief introduction why leakage power is important. Okay, why should we reduce the leakage power? So the question leakage, so just this are the I will explain Telugu also. So threshold leakage current తగ్గించడానికి మనకి ఉన్న బేసిక్ రీజన్స్ ఏంటంటే లీకేజ్ పవర్ అనేది జనరల్లీ ప్రీవియస్ కన్సిడరేషన్ మనకి 90 నానోమీటర్స్ రేంజ్లో లీకేజ్ పవర్ పెద్ద ప్రాబ్లం కాదు, ఎందుకంటే వీఆర్ నెగ్లెక్టింగ్, ఎందుకంటే డామినెంట్ పవర్ అనేది మోస్ట్లీ మనకి డైనమిక్ పవర్ డిస్పేషన్ ఎక్కువ ఉంది. బట్ యాజ్ ద టెక్నాలజీ ఇంక్రీజ్ అయ్యేసి డివైజెస్ ఇంకా చిన్న స్మాల్ సైజ్లో మనం మ్యానుఫ్యాక్చర్ చేసే టైంలో ఈ లీకేజ్ కరెంట్ అని చాలా డ్రాస్టిక్గా ఇంక్రీజ్ అవుతుంది. At that time this is a very important parameter, ఎందుకంటే we are providing very supply voltage is also very small. ఆ చిన్న స్మాల్ voltages లో if you are still some leakage is increases means that obviously battery life is also decreases. So for that purpose you have to keep that point, you have to reduce the corresponding leakage current. So that's why it is also one more important. As well as if you want to design a good system, obviously we are expecting a performance. So the performance is increases by decreasing the delay value. The delay can be decreases with respect to the corresponding threshold voltage. That means if the threshold voltage is decreases means that delay is decreases. As the delay value is decreases means that performance is increases. That is the second conclusion, right? As well as so that's why as well as leakage current point of view means that if you are increasing the threshold voltage, leakage current is decreases. From this graph, it is one more important one. If you are decreasing the threshold voltage, obviously the delay is decreases. As the delay decreases means that performance is increases. These are the two important points you have to remember before going for the fabrication of the multiple threshold voltages within a single chip. Okay, so thank you for watching GMK tutorials. Thanks you.